Picture this. A single bolt of lightning slashes through the sky, dazzling and terrifying all at once. In just milliseconds, that bolt generates heat 5 times hotter than the surface of the sun. 5 times hotter than the sun. How is that even possible? What's going on in those fleeting moments of raw power? And more importantly, why doesn't the Earth just ignite from such intense heat? Stick around, because this is one science fact that's going to blow your mind. Lightning, one of nature's most jaw-dropping spectacles. We've all seen it streak across the sky, lighting up the clouds and roaring with thunder. But there's so much more to it than just a flash and a bang. Each lightning bolt is a violent discharge of electricity, powerful enough to split the air apart and create temperatures that make the sun's surface seem like a warm bath. Now, here's the kicker. A single strike carries enough energy to power a 100-watt light bulb for over 3 months. Yet, it's over in an instant. Why is it so hot? How does it form? And why don't we feel its full force when it strikes the ground, or even a person? In this video, we'll break it all down. The physics, the myths, and the mind-bending science behind lightning. Let's start with a question that's puzzled scientists and thrilled nature enthusiasts alike. How can something so brief, a flash lasting less than a second, produce heat hotter than the sun's surface? To put that in perspective, the surface of the sun burns at about 6,000 Kelvin. A lightning bolt? 30,000 Kelvin. That's a scorching difference. But here's where it gets tricky. Even though it's that hot, the energy is concentrated in such a small space that most of us can't feel its full intensity. Instead, we experience the aftermath, charred tree trunks, cracked sidewalks, or the thunderous clap that follows. So, here's the challenge. Understanding how something so short-lived can generate such extreme temperatures and cause so much destruction, all without vaporizing everything around it. And here's another challenge, harnessing this raw power. With nearly 8 million lightning strikes hitting the Earth every day, imagine if we could capture even a fraction of that energy. Could lightning become the ultimate renewable resource? Or is it simply too chaotic and unpredictable to control? To answer these questions, we need to understand what lightning really is. Lightning begins with a thunderstorm. Inside the storm, winds toss water droplets and ice particles around like a blender on high speed. As these particles collide, they transfer electrical charges. Over time, this creates a massive imbalance. Positively charged particles gather at the top of the storm cloud, while negatively charged particles sink to the bottom. When this imbalance becomes too great, nature has to fix it. That's when lightning happens. It's essentially the atmosphere saying, okay, time to restore balance. A sudden, intense flow of electricity leaps through the air, neutralizing the charge difference. But why is it so hot? The key lies in the sheer speed and force of the process. When lightning strikes, it compresses and heats the air around it to extreme levels, creating a plasma, a superheated, electrically charged state of matter. Plasma is rare on Earth, but it's common in stars, which is why lightning shares a bit of the sun's fiery nature. Let's go deeper. The incredible heat of lightning happens because of electrical resistance. As electricity travels through the atmosphere, it faces resistance, and that resistance generates heat. Think of it like friction. When you rub your hands together quickly, they get warm. Now imagine that on a cosmic scale, with billions of volts of electricity squeezing through a narrow channel of air. The result? A temperature that can melt even the toughest metals. And here's a fun fact. The heat from lightning is so intense that it can fuse sand and soil into glass-like formations called fulgurites. These natural sculptures are a reminder of the raw power packed into every bolt. Now, here's the big question. Could we ever harness this energy? After all, a single lightning strike can carry up to 1 billion joules of energy. That's enough to power a small house for weeks. But before we get too excited, there's a catch. Lightning is incredibly unpredictable. It doesn't strike the same place twice, well, unless you're talking about places like the Empire State Building, which gets hit up to 25 times a year. Scientists have tried to develop ways to capture lightning's energy, but so far, it's like trying to bottle a tornado. The equipment would need to withstand the heat, the voltage, and the sheer force of a lightning strike. And even if we could capture it, there's the problem of storage. How do you store billions of joules of energy in a split second? But that hasn't stopped researchers from dreaming. One idea involves using tall towers with conductive materials to guide lightning strikes into massive capacitors, which could store the energy for later use. Another concept explores using lightning as a direct power source for remote systems, like weather stations or satellites. Still, the unpredictability of lightning makes it a tough nut to crack. For now, we can only watch in awe as this natural phenomenon lights up the sky and reminds us of the raw power that exists all around us. So, what's the takeaway here? Lightning is one of nature's most powerful and mysterious forces. It heats the air to temperatures hotter than the sun, creates glass sculptures out of sand, and generates enough energy to power a home for days, all in a fraction of a second. While we may not be able to harness its energy yet, studying lightning helps us understand the incredible forces at play in our atmosphere and pushes the boundaries of science and technology. And the next time you see a storm roll in, you'll know that each bolt of lightning isn't just a spectacle, it's a moment of pure, untamed power.